This example is from section 3.6, which talks about derivatives as rates of change. To put that another way, this section looks at examples where we specifically talk about the derivative as the rate of change of some physical phenomenon, maybe some economic situation. But derivatives, after all, are rates of change. Calculus we can think of as, really describing how things change. And that's kind of the theme of this particular section. We really don't see any new rules in section 3.6, but it's being able to take the things that we've learned before and really think about derivatives in a more contextual type of example. Here, in this example, we're looking at the graph of a position function. And I apologize for my my handwriting here, but let me read through this and we'll work our way through this together. So this is the graph of S equals f of t, represents the position of an object moving along a line at time t greater than or equal to 0. So this is a position function. We're going to imagine this keeps going, beyond what's drawn here, but starting at 0 and then for all time greater than or equal to 0. A says, assume the velocity of the object is 0 when t equals 0. For what other values of t is the velocity of the object 0? Okay. So in order to answer this question and the rest of this problem, the important thing to understand is that velocity represents the derivative of position. Okay. So we've got this position function. They're asking us where is its derivative equal to 0. Okay. And so to answer that, what we want to think about is, as we look at this graph, where would it have a horizontal tangent line? Okay, so if you look at this graph and kind of give that some thought, the place where it's going to have horizontal tangent line is going to be at those turning points. Okay, so where it's the position is here, and then it reaches this peak, and then it starts to decline again. Okay, well, right at that transition point is a place where the velocity is 0. So the answer to this is going to be t equals 1, t equals 2, and t equals 3. Those are the three places where we see the graph turn like that. In other words, where it would have a horizontal tangent line. Part B says, when is the object moving in the positive direction and when is it moving in the negative direction? Okay. So, again, what we need to understand is that velocity is the derivative of position. So when it says when is it moving in the positive direction, another way to ask that would be, when is the velocity positive? And when is the velocity negative? Okay. So I'm going to say v is greater than 0. Okay, so velocity is greater than 0 when, okay, and the answer to that is when the graph is rising. Okay, when it would have a positive slope for its tangent line. So that's going to be from zero to 1, and also from 2 to 3. And v will be less than 0, that is, the object will be moving in the negative direction when t is between 1 and 2, when the graph is falling right here, or when t is greater than 3. Okay. All right, so again, just like in part A, the important thing to understand is the connection here between position and velocity. C says sketch a graph of the velocity function. I'm going to sketch it right over here in a different color. And a lot of times students that are learning calculus find graphing derivatives challenging. And it is challenging. Here's what I would recommend as a starting point. Exactly what we talked about in part A is first think about where is the derivative going to be 0. And we said that that's at 1, 2, and 3. So I'll plot those zeros on the graph. We also were told to assume that it's 0 at 0. The part B of this problem had us looking at where is it going to be positive and where is it going to be negative. Okay. Now, I don't want to focus too much on how positive and how negative it should be. That's really fine-tuning the graph, and I'm not saying that it's unimportant. I will take it into consideration here, but I'm not going to worry too much about getting that magnitude down, very precisely, because we really don't have a lot to go on here. The s-axis or the y-axis here is not labeled. But I will say this, and this is something we'll see more in chapter 4. The highest point positive here between 0 and 1 will coincide with where the position graph is rising most steeply. Okay, so I'm going to say, between here and here, it might look something like that. We know it's going to be positive, and it starts out 0, it ends up 0, and where it starts to fall is where the graph starts to become less steep, the graph of the position function. Okay. And likewise, we're going to see a portion of the graph between 1 and 2 where the velocity is negative because the position is decreasing. Now between 2 and 3, notice it gets a little bit more steep than it does between 0 and 1. So that would suggest that the velocity function goes a little bit higher between 2 and 3 than it does between 0 and 1. And again, precisely what the magnitude is in terms of this graph, I'm not going to concern myself too much about that right now, but relative to what we see between 0 and 1, this is going to rise up a little higher. The most important thing from my perspective that you should become comfortable with in terms of sketching this is first knowing where the zeros are and knowing where it's positive and negative. If you become comfortable with that part of it, you've gone a long way toward understanding how derivatives should look. There's more to it, of course, than that, but that's a really big part of having a derivative that looks correct for the original function. And then here we're going to see something where it remains negative, and if this continues to become more the position, if it becomes more and more steep in its decline, then that means the velocity function will get further and further away from 0. Okay, so that's roughly what the derivative should look like. Finally, part D says, on what intervals is the speed increasing? Okay, now speed here is the absolute value of velocity. Or to think of it another way, speed is what you're talking about when you ignore direction you take velocity and take away the direction part of it, which in this case would mean just ignore the sign. That's the speed. And the speed is going to be increasing, okay, when the magnitude of the velocity graph is increasing. So as the velocity becomes further and further away from zero. Now, we're going to have to estimate a little bit here, but I'm going to assume these peaks here come halfway between those zeros, which is roughly what it appears to be the case. So we can say the speed is increasing between 0 and 1/2 because velocity is getting further and further away from 0. To put that another way, the position function is getting more steep. The tangent to the position function is getting more steep. Now, we also see between 1 and 1.5, the velocity graph is also getting further and further away from 0. Now, it's going in the negative direction in that case, but remember with speed, we're not concerned with direction. Okay, and then finally between 2 and 2.5, so between 2 and 5/2. Okay, now lastly, beyond 3, so t is greater than 3, we also see that the velocity graph is getting further and further away from 0. And another way to say that is the object is speeding up. Okay, so that completes that problem. Again, here the focus is to take these concepts that we've been looking at through chapter 3 of the derivative and really put them in some context. And position velocity is a very important example of taking the derivative concept and putting it into a real context. I hope that helped. See you in the next video.